So hello, thank you for coming in this sort of miserable weather. So I've been trying to emphasize, starting with local, going to global, what this means. And I talked about it in a concrete case where U is, say, an open set in the complex plane, but we will very shortly go to a manifold situation. And we take point in U, so U draw a picture like this. Yesterday I drew a picture with some holes. And my wrinkles. And we take Z in U and we look locally. So in fact, I'm going to make a covering, so take Zi in U. So make a little cover, we're going to make a covering. So here's Zi. And we look in the local ring at Zi. And you know what that is, that's a power series ring and a convergent power series and so on. And this is a unique factorization domain. So that means that there are no divisors of 0, and so let me write this because we don't have so much experience. It means that f times g equals 0 implies that f equals 0 or g equals 0 in this local ring, and it implies unique factorization into primes up to units. So I always write a unit here, so you can always multiply by a unit, it doesn't change anything. But you have up to order and up to unit, you have unique factorization. And what that means is that, as you know from elementary lectures, that you go to the quotient field of this thing. And what that means for us in complex analysis. So always look at the algebra first to make sure you understand what the algebraic structures are going on. And for us in complex analysis, it means we can find coordinates well, it's a coordinate because it's only one dimension. I'll call it Z. It's not the linear coordinate Z of the plane, but I'll call it Z, the local coordinate Z locally. So that if you take M in the quotient field of this integral domain, then M is equal to Z minus Zi to the order of M. And you should really write at Zi, right? Because it depends where you are. You move away from Zi, you get different order. And this order now is, as you know, I'm just repeating things you know, is no longer positive or 0, it's an integer. So it maybe is negative. Yeah. And if this thing is negative, then we say, by definition, M has a pole of order n. Well, okay, of order O. At this point Zi. So we went to the quotient field, and we have these poles possible here, and we have this little disk here where n is defined. Really, I took a representative here in the local ring, but n is defined as a quotient of power series. There's nothing special about it. Right? And that's as a pole of water. And if m is positive, if this thing is positive, then we say m has a 0 order of order ON. And otherwise, it's a unit. And in some sense, otherwise you don't care. Because the units you can do anything with. You can invert, go up and down. It's zeros and poles, it's really what matters. And in some sense, they're equivalent. That the poles of 1 over n equal the zeros of n. So in some sense, there's some right. There's some balance here that poles and zeros don't matter. There's an equivalence here of that we'll understand much better later. So that's really the local ring discussion. I mean, that's the end of the algebra. That's the end of the algebra. And so we now what we do is we take a covering. I use script U always to denote a covering here. Where in fact Mi is of the above form on Ui. And even more generally, Mi, let's just say, is Fi over Gi, where Gi is nowhere locally 0. So even more generally, so not just in the local ring and not just in a little neighborhood on a disk, just anything. Mi is just a quotient where Gi is nowhere locally 0.
So does it mean that it's also not 0 at Zi?
No. Thank you for the question. There are two notions. Locally 0 means it's identically 0 in a neighborhood of. That's what I mean by locally 0. And 0 at a point means its evaluation at that point is the number 0. And of course, we have these quotients. I want that possibility because it's going to be a pole, but I'm happy for your question. I always, in some sense, I always forget the statement, nowhere locally 0. I just forget it. But in fact, you don't want to be stupid and divide by something that's identically 0. Right? That's what I'm saying. Don't be stupid. Okay, so we have that situation. And then what we have is we have, this gives us a covering U and a collection of meromorphic, a collection of quotients M, a collection of quotients. So a covering U equals Ui and a collection of quotients. And I'm really thinking absolutely locally in the quotients in this local ring, but maybe more generally, M, a question of these quotients. Yeah. So that's very local. You have no other condition. Okay, that's something that my grandson can just write down. But at age 7, yeah. But now we have an equivalence relation, right? We have an equivalence relation. So we want to define another condition, not yet an equivalence relation. Mi restricted to Uij equals mj restricted to uij. Right, I mean, uij is the intersection, I always write there, right? I mean, this is the obvious thing to do, that you want these things to piece together. So this, you go from local to global, now we're really global if that happens. So it's a covering, a bunch of quotients, this condition. And this whole thing together is a meromorphic function. On U. Okay. Locally, it's good. You love it. It's quotient. It's just like the rational numbers. Locally, it's 1/4, or right, something like this. And then you have this everywhere locally, and then you guarantee everything is good by saying it pieces together. And then there's a big caveat. A priori, at least. Let's call this whole thing meromorphic function, let's call it M. Caveat M is not necessarily quotient of two holomorphic functions. A priori. I don't know a priori. Do you understand what I mean by a priori? I don't know. I'm standing here in the room, but I really don't know. Right? Maybe not. Maybe not. Okay. So that's problem number 1 in series complex analysis. You see this in the work of Poincaré, and it's in the work of many people. So problem 1, number 1, given M meromorphic on U, and I will change U to a much more general object later on, a complex manifold or whatever, but here just a domain. Given a meromorphic function on a domain in the complex plane, for example, are there holomorphic functions F and G in OU such that M equals F over G. And we can more or less formulate this in the following way. Is M U question the quotient field? I don't know your note. You must tell me. I think what is Pinkoff used for the quotient field? Do you know? Remember? Okay. The quotient field of OU. This is a more general question. This is maybe some meromorphic functions are globally quotient, but maybe not all. So this is a different question, slightly different question. This is a statement that everyone is a quotient. And you can ask relatively prime, just like you say, I require it to be 1/3 and not 2/6. Right? So that's an obvious problem. Right? Okay. Now, this problem is non-trivial, so we go to some very interesting derived characteristics of meromorphic functions. And the classical words that you will need to learn to to impress your neighbors. The two words, divisors and principal parts. Now, I will explain this. And I will have problem number 2 in complex analysis and problem number 3 in complex analysis, which are the 3 main problems that I want to discuss in this course, which is called topics in complex analysis. Okay. Now, you know, this is the correct spelling of this, by the way. It's very hard to remember this, also for me, because we talk about the maximum principle, the identity principle, all of these things. But now I'm looking at the way to remember this. I'm looking at APIC, and in complex analysis, he is he. So, whenever anything is important, whenever it's the main thing, yeah, that's the way you remember the word principle, the main thing, right? Right? You just think about it. Okay, we've got it. Right? Yeah. Okay. So these are the 2 things I want to talk about right away. And so, to talk about this stuff, I go back to the local ring. And I know that I have some meromorphic function, and I'll write it here as z to some order. And I don't worry about the local normal form. I have times the unit. Right? So no local normal form here, just z to some order times the unit. So in any coordinate system, well, let's even, let's say even m of the base point. Let's even put something here. Let's put a number here. I don't know, number a. So this is local normal form. No, I don't want. Yeah, I want any coordinate. Okay. So I want to say this thing equals 0 is allowed. Okay, and now I have any normal form, right? Any coordinate. Now, in mathematics, you should do everything conceptually and do as much as possible without coordinates to introduce the appropriate concept. So the key concept here is the order, right? -1, 2, 0, and so on. This association is allowed. So in some sense, what is allowed, I mean, it's a well-defined canonical association. Maybe let's make it more precise. M at a point at zi, one of these covering points, m is equal to z minus zi to the order times the unit of z. And again, this, as I said, this thing is canonical. It's canonically associated to m. To m at z. Right? Right? So if you like, I can do this at every point. This really gets on my nerves. So what I have here is at every point I have an integer O of m, and O of m, and let me emphasize, and z, depending on the point. Right? I wrote zi here, depending on the point. Right? So just think of this, walk around and think of this at night time, At this point, I have minus 2, and then it goes to 0. Because if I have minus 2 here, I have to have 0 nearby, right? Because the normal form will tell me nearby is a unit. And I walk around at nighttime and smoking a cigar, drinking cognac, and then I come here to plus 1, right? At another point, minus 2 plus 1, it's mostly 0, right? So, and these points where it's not 0 is a discrete set, right? These points cannot accumulate because that violates the identity principle, right? So I'm assuming this function is not constant. Okay, so here it has a pole of order 2 and then nearby 0, and nothing's nothing, here a 0 of order 1, nothing, a pole of order 17 and so on, right? So there are two ways of looking at this. Two ways of looking at this thing. One way of looking at this thing is the viewpoint of Hermann Weyl, and we call this a Weyl divisor. Not Hermann Weyl, Andre Weyl. Andre Weyl. So I go back and forth between Hermann Weyl and Andre Weyl. They're not related to each other at all, although they're probably more or less the same name. If somebody is a specialist in the meanings of these names, I don't know, they're probably the same name. Anyway, both great intellectuals. Hermann Weyl, even born in the 19th century, Andre Weyl, much more modern. I experienced Andre Weyl, so example that tells you, I don't know. He would maybe be about 100 years old now. He's a wonderful mathematician who tried to make many things precise in algebraic geometry, for example, number theory, and complex geometry. A Weyl divisor is a mapping x to z with discrete support. What did I just tell you? I told you, whoa, what does support mean? Support in this case means where it's not 0, right? Okay. If you're talking about support of continuous functions or smooth functions, it means the closure of the set where it's not 0, where it's not 0. So, but this set is discrete, so it's closed. Okay. So in general, the good definition of support means the closure of the set where it's not 0, right? If you have a function that looks like this, particularly a cutoff function, something like this, right? Yeah. You ask, and then 0 here, and you ask what is the support of this cutoff function? The cutoff function is of course 0 here and 0 here, but it's support. You put these numbers in the support, and the reason is if you take a neighborhood here of anything, you're going to hit someplace where it's not 0, right? So this is a key notion of support. The support is equal. The support is equal to the closed interval. This is f. Well, I always call cutoff function chi. Support of chi is the closed interval. So the support, discrete support, you don't need to use the words closed because it's already closed because it's discrete. Okay. So it has discrete support. It's just a map. If you wish, this is called the map, the order map in the above case. But I want to consider any Weyl divisor, Andre Weyl divisor. Any Weyl divisor will be just anything like this with discrete support. Okay? No objections. Okay? So that's the easiest thing to understand. And so if we have the divisors in the sense of Andre A is what we have here, all possible divisors, right? And it's very interesting. This is all possible divisor. This is a multiplicative group. Now, what is multiplication? What does multiplication mean? For me, it's multiplication. I mean, it's a group. It's pretty obvious what you do. If you have one divisor and it's these various things at various points, and you have another one, you just multiply them together as a function. As a function. Right? Well, it's dangerous. It's dangerous. Is it a multiplicative group? No. It's an additive group. In this formulation, it's an additive group. Right? Because if you multiply someplace, one divisor might be 0 here and the other divisor not 0, then I kill that point. That would be stupid. So yeah, I'm thinking something else. This is an additive. Don't tell my grandson that I get mixed up between multiplication and addition. He doesn't. This is an additive group, right? You could, yeah. This is what you want. Okay. And also, it's completely obvious that if you have, well, that's x. I don't know what x is here, but x will be later. This will be, well, maybe. Let's keep the notation reasonable. Let's call this u. It's anything, but. Let's stay with the plane. And we have a mapping from meromorphic functions to divisors. Right? And the mapping is, if you take a meromorphic function, you go to its divisor. Right? Every meromorphic function. I've talked, what is the divisor of a meromorphic function? I told you what it is. It's this order thing here, right? Now, of course, I make a mistake always. Well, maybe I didn't make a mistake. It's a question if you allow a divisor to be identically 0 or not. Everywhere is 0. Oh, why not?
Discrete support.
Hmm?
Discrete support, right?
Yeah, let's think about that. Yeah, that has discrete support. Is what I'm saying. Principal part come here. It's okay to be identically 0. However, if you take oh yes. Yeah, the constants go to 0. Go to the 0. Yeah, yeah. And it's clear, right? If you take the divisor of m1 times m2, it's okay. Here we go. Here we go. It's the divisor of of m1 plus the divisor of m2. Right? Is that right? Right? Because all this is saying is the order of m1 times m2 is equal to the order of m1 plus the order of m2. Right? Right? And when I write it this way, I would like to say it's okay to write this thing as with respect to addition, and write this thing with respect to multiplication, and therefore I should not have the identically, should I have multiplication as a group morphism, I think of this as just multiplication group morphism. I look at the multiplicative group of meromorphic functions, yes? I'm thinking about this, look, this is the multiplicative group of meromorphic functions, therefore I must throw out the identically zero guy, because I can't take one divided by I can't take one over it, yes? So we have the multiplicative group of meromorphic functions goes to the additive group of divisors. So in our lingo here, we put a star here. As you know, if you have the field, this is a field. This is a field. So you have big choice as what is the group. You can add, and addition is wrong from the point of view of divisors. Or you can multiply, and multiply is right, but if you're going to multiply and thinking of it as a group, you should take out 0, and taking out 0 means you put a star here in your notation. You know this, right? C star is the multiplicative group of C, and K star is the multiplicative group of any field K. Okay? And so what we do here is we pull out the identically zero function so that you have a mapping from meromorphic functions to divisors. Okay? Now there's another Bourbaki guy, whom I also know. I think he's still living, Cartier. Oh, by the way, one of the most wonderful lecturers and writers in Bourbaki. So Cartier pointed out this is, you should formulate in a better way Cartier divided. Okay, and I will tell you, it doesn't matter in this case, but I think Cartier's, it matters in general, by the way, but I think Cartier's viewpoint is better. So, the reason Cartier's viewpoint is better, it doesn't require really any discussion of order to define it. We say M1 is equivalent at Z to M2. I'm going to tell you when two meromorphic functions are equivalent at a point, right? Guess what? They have the same divisor. Okay? If and only if, this is Cartier's definition, if and only if M1 divided by M2 is non-vanishing holomorphic at Z. Get it? That means M1 and M2 really have to have the same zeros and poles. It means that, yeah? It means I don't care about the units. So I killed the unit with this equivalence relation, right? M1 divided by M2 is a unit, right? Now, you see that it's going to be more or less the same thing that I'm getting here. That means that in some coordinate system, whatever coordinate system you choose, the order of this guy and the order of this guy is going to be the same. But that requires discussing coordinates and all sorts of stuff, and is a very bad idea. So the Day definition is, in my mind, not nearly as good as the Cartier definition. Yes?
What does the star above the...
Again, star means, thank you. It means, the units equals the set of F in OZ such that F at Z is not equal to 0. Equals the set of F in OZ such that 1 over F is a known. Okay. Right. The units. It says that up to a unit they're the same. This is a very good definition. Up to a unit, these functions are the same. Right? That is a very good way of thinking. That's the local way of thinking. Locally, up at this point, up to a unit, they're the same. Okay. Okay. And now we have the Cartier divisors. Cartier divisors on a covering. Right? So on UI, on a covering, what on an open set, what does that mean? On an open set, not just on an open set. What should that mean? That should mean you have a covering, and equivalence classes of meromorphic functions on the cover on this covering. So let me just write equivalence classes of meromorphic functions on this covering. Right? So Cartier equivalence. Right? So covering, equivalence class of the covering. And on the UI. So let's put MI here on UI. Yeah, with compatibility. So in other words, D of so let's call this thing D. I don't know what to call it. Give me a suggestion of what to call this terrible thing. The divisor on the covering represented by the meromorphic functions. Okay. That's too much writing, right? You have a covering on each open set, you have a divisor, yes? And yes, and with compatibility. That means that the divisor at well, DI. Oh, I see. I know what I will do then. I will write here DI. That's much better, isn't it? No, I will write here even better. Script D. Okay. So you see, I'm reminded of the German language for the word for lecture. The word for lecture in the German language is two Germans that tell you is Vorlesung. And Vorlesung means to read, you read for. This means if you go into the church and the pastor or the priest is reading the Bible to you. This is what a Vorlesung is, and it was, you may not know this, maybe Germans don't even know this. In the even after World War II, there were essentially no books, and there was no internet, there was nothing like this. And so the professor would write a script and read it for. So a Vorlesung was, the professor would stand here with his script that he had written perfectly, and take the script to the board. Literally, Vorlesung. So the professor was not important. He was just taking his script to the board, right? Yeah. I don't believe, as you can see the way I lecture, I don't believe in that. I believe in the dynamic of a lecture, particularly nowadays, because there are so many beautiful scripts on the internet. You can find anything you want. Anything I say, maybe this viewpoint I'm saying here today is not particularly exactly on the internet, but people who look at things on the internet will tell you you can find anything, and there are many books. So the notion of Vorlesung is vorbei. It means you can forget it. Forget it, right? But it is interesting. We have this notion of divisor, a Cartier divisor on U. So a Cartier divisor on, a representative of a Cartier divisor on of U. Well, let's see here, let's try it. Equals equivalence classes of coverings and divisors defined on the covering. Hey, I got it. That's a script D. Yeah, you like it finally, right? This is good. You see, this is not some stupid calculation, it's understanding how to define something right. Yeah? You have a covering, right? On each element of the covering, you have a divisor D, DI. Yes. On the overlap, DI is equal to DJ as a divisor, right? And you take the equivalence, so DI and DJ in D, then compatibility is DI restricted to UIJ equals DJ restricted to UIJ, right? It's the same as always, local to global, right? On each open set, you have this divisor, right? On the restrictions, they're compatible. And this gives you a representative of this divisor. And then you take equivalence classes of these divisors, and that of these representatives, and that means you take two coverings, two representations, you take a refinement of the coverings, and they should be the same, or equivalent. And equivalence is obvious what that means, right? Okay. So in some sense, you can see when you can see why people prefer André Weil to Cartier, because André Weil just associates some number, right? Is some number, right? Abe got mad at me when his last name is good because we think of principal things, but he got mad at me when I said, well, it's just the free abelian group generated by you. Do you understand what I mean? You take, what does it mean, the free abelian group generated by something? You have a set, and you just take it's ridiculous. You just have a set, and you just look at the group generated by that, right? No relations. Everything commutes. Everything commutes, right? So, right? So you see, it's the free André Weil divisor is this. You take the set, which is U. You take the free. Wait a minute. Wait a minute. It has only finite support if you do it that way, right? Because the free abelian group, I think, is by definition only finite letters. Who's an algebra expert here? Who's interested? You understand what I mean? You take a set, and then you take the group generated by that set, but that doesn't make any sense at all because you don't know what the relationships, whether they commute or not or something. But you define them to commute. Yes? And the trouble with these devices, they may have infinite support, right? Yes? And that's the non-trivial case. So it's not necessarily, it's very close to the free abelian group generated by this thing, but not quite. It's somehow the completion of the free abelian. Okay. So Cartier is that. That means you have divisors. That means you have problem number 2. Problem number 2. Either way, this is the same definition. This says you have the meromorphic map functions on U. You look at the multiplicative group. Well, maybe not. Yes, I want this to be a group morphism to the divisors on U. So M is mapped to its divisor. what do I call it, problem number 2. I call this is the mapping view, problem number 2. Determine the image of div, and e.g. is div subjective. Well, that's an interesting question. Elise hands me a divisor. Maybe even, you like this discrete set of points. So Elise hands me, here's you, it's some terrible thing. Elise hands me this thing, it's a sequence of points, the support. And here you have a pole order, I don't know, let's just write, poles and zeros are the same, M1, M2, M3. Maybe he's perverse, this German word perverse, I don't know. If you say, you see, if you say, translate that as perverted into English, it sounds very heavy. Yes? But to do something perverse in German is really, can be just sort of crazy.
It also sounds bad.
Huh?
It also sounds bad.
Yeah, it's pretty tough. But this is, let's use the German word. It's perverse here if the Elise will hand me a divisor that accumulates, its support accumulates every boundary point. You might think of that. I mean, your computer science, your life is finite. So you hand me a finite divisor, and I'm stupid. I can easily solve this problem. I just write down ratios of polynomials. This is stupid. So if Elise hands me a finite computer science divisor, I say it's not serious. Hand me something more subtle. And then he hands me something perverse. And that means, I think you would agree that this is perverse if it accumulates at every boundary point. Yes? You can organize that, right? It's not hard to organize, right? So it could be really, right? You can imagine, it's not so hard to organize that. So it's a question of whether, in that case, whether it's subjective. That's an interesting question. That's problem number 2, yes.
So do we distinguish between Cartier and...
No, they're the same. No, I thought that was implicit here. It's exactly the same in this case. I just wanted to put it in your heads that in general it's not the same, and that somehow this is Cartier is a much more natural definition. Because you see locally it's the divisor of a meromorphic function. Is it globally the divisor of a meromorphic function? Right, that's sort of the local global question, which is, and it's a coordinate-free definition in some sense. Right? It's much better from our point of view. But
did we define the Cartier divisors on a set? Like on our domain?
On you, yeah, sure. Just take, I told you how to do it. Take a covering.
Okay.
Take a covering on each, then you have to say when 2 meromorphic functions are equivalent because you've taken a covering. But that's stupid. It's just they're equivalent if their ratio doesn't vanish or has no poles. Mm-hmm. All right? Yeah. Okay. This is somehow the fundamental problem. In non-compact analysis, this would be called a problem which was discussed in great detail by Karl Weierstrass, who, by the way, grew up very close to Bremen, not very far from him. Okay. Problem number 2. And now to problem number 3, which involves APIC, principal parts. Now, Weierstrass is multiplicative. You see, it's multiplicative because you really want to, you have this morphism which is multiplicative. It really sends m1 times m2 to the divisor of m1 plus the divisor of m2, right? You have to think of, I regard that as a multiplicative problem. I regard Abig's problem as the additive problem. Abig's problem is actually very close to the logarithm of the multiplicative problem. You will see through a deep observation. But, okay, you have multiplicative and additive. It's called the exponential method. Okay, so we're going to go to the notion of principal part. I say, well, you see, this is the reason Cartier is good. Let me put here Abig. I will change this later on, but just for the purposes of this, Abig would define the same if and only if, because he likes additive. M1 minus M2 is holomorphic. Abig at Z. Right. And remember, M1 equivalent to Cartier at Z, if and only if M1 divided by M2 is holomorphic and has no zero. You see, this is the multiplicative problem, and this is an additive situation. It's additive, right? The difference should be holomorphic. Okay? And the equivalence class then, the equivalence class of a meromorphic function at Z is the equivalence class, the above equivalence class. It's Abig. Let's see if I get your name spelled right. A-B-P-I-K?
ABH.
A-B-H?
Yes.
Abig.
Yes.
I-K. Great. I'm sure I'm pronouncing it wrong, but it doesn't matter. So there's an Abig's equivalence relation. Okay? But we will now write it in the language of our lecture. This is called the principal part of M at Z. Okay. Okay. And now, I'll tell you how my professor some years ago, who was a wonderful man, and I've spoken about him before, the way Max Schiffer would always write this. Very good complex analysis in one variable. He would write, Max Schiffer would write, say at the point at 0, he would write M equals A minus n, say minus n over z to the n plus A minus 1 over z plus holomorphic terms. Well, a meromorphic function locally in the local ring is a quotient of two local functions. The top has a power series development and the bottom also, so you have to decide whether you have a pole or a zero. Let's suppose you have a pole. That's because the only interesting thing here is when you have a pole. Right? So that means the degree of the bottom is bigger than the degree of the top. Right? So you start dividing by z. So you have the power series of the top divided by some power z to the n. And that gives you the principal part plus holomorphic terms. Right? And the equivalence class of the principal part plus holomorphic terms is the same thing as the equivalence class of this part here, of Abig's part. But when you write it that way, it's very heavy coordinate dependent. But if you just say there's a equivalence relation, it doesn't depend on anything. Right? Okay. So that's the relation. And then so kind. Probably one of you. And then you have the same definitions as before. All of these definitions probably in the German school, either in Göttingen or Berlin, in this case probably Berlin, in the School of Bioscience. Weierstrass grew up around here, not far from here. If you want to know, you go on the train from here to Münster. Maybe some of you have taken the train from Münster, Bremen to Münster, right? And you have a stretch not so far. You go through Osnabrück, and in there are some small towns, and there's where Weierstrass grew up. And in those days, in the 19th century, every father wanted the son to study something like law or theology or something like this. Ridiculous. And so his father, Weierstrass' father, sent him to Bonn, where I live, near where I live, and told him to study something like theology. And so, you know, it's typical, study theology. It's ridiculous. And Weierstrass hated that. So at nighttime, he would get a light somehow under the cover and try to understand deep mathematics. And then finally he convinced his father that he should be allowed to study mathematics. And so he made a deal with his father, probably with his mother. I know my wife, so I know how it goes. That he'd have to come closer to his home. So he studied mathematics in Münster and got his degree in Münster. Of course, in those days, you needed a job. You couldn't become a consultant for some finance agency or cryptology or something, and so on. So he got his teachers to become a teacher, and he actually became a teacher. It's a very long story. It's a beautiful story. He ended up being absolutely a boss in Germany, the rector of the University of Berlin. Very, very important in proving, of course, as you know, very deep theorems. He put Riemann on the map precisely. Riemann was more or less thought in terms of physics. He believed these things exist for reasons of physics, and he was usually right. But Weierstrass says you have to prove convergence, you have to do this, you have to do that. So if you read Weierstrass' lectures in Berlin, I've read one of his full lectures in complex analysis, more advanced than this a little bit. In 1876, I read it, and particularly Germans should read it because it's in a modern German. This is not so clear. In 1876, he would write in modern German, completely modern German, Hochdeutsch, modern, completely modern mathematics, everything proved, perfect, incredible. Very difficult to do that. Imagine doing that. So that was Weierstrass, and at this time, maybe this problem would be called Weierstrass problem. And now he had a student. So, just like Appig, he was a student. Who was actually Swedish background. Named Mittag Leffler. And Weierstrass had a number of very good students. He was one, and he eventually had great, maybe didn't prove a huge amount of mathematics, but had very important influence in mathematics. I can tell you some stories about him. Yeah? So, and I call this Mittag Leffler problem. And this will be problem number 3. So I want to emphasize in this lecture, I'm not proof a thing, but I have told you, I will tell you 3 fundamental problems. every meromorphic function a quotient of two holomorphic functions? Is every divisor a divisor of a meromorphic, globally defined meromorphic function? Okay? You can imagine what this third problem is going to be if I've made this motivation additive motivation. Yes? So I have to talk about here about Abig's equivalence relation. And so I introduce something called H of U. And script H is always big for me. When I write script, it means it's some big say. Yeah. And this is not devoted to my last name, but it is devoted to Hauptteil. You have to know these German words in mathematics. So, for example, the great French mathematician Henri Cartan said, if you want to do complex analysis, you must learn German. And there's a reason for that, because as you see, the foundation of a lot of this stuff is completely German, and in higher dimensions also. I think that was Cartan, but of course Cartan understood German. So this is so the German word is Hauptteil. And you see, one reason to learn German is you want to learn long words. It's really fun to learn long words. Hauptteilverteilung means distribution of principal parts. Haupt means main. So that's the way to remember principal spelled with Apik means Haupt. You're the main guy. Yeah? And so Hauptteil, so principal part, distribution. So a distribution of these things, which was given here when we were talking about object later. Okay, a distribution of these things. It means instead of prescribing multiplicative stuff at points, you prescribe the polar behavior at such a point. Okay. Well, there it is. There's the equivalence relation. M1 is equivalent to M2 if and only if the difference is holomorphic. So that's prescribing the polar behavior at the point. Okay. So what is it? What is such a thing? So again, it's a terrible thing. It's an equivalence. So you have a covering, and you have a Hauptteil on this covering. So what this means is, it means on every UI, we have H of UI, which is an equivalence is M of UI modulo additive equivalence. So I'll write here Apik. I got it right. So modulo additive equivalence on the meromorphic functions on UI. That's this thing. Yes? That's this thing on a covering and equivalence relation where refinements, etc. Do you understand what I mean? You refine the covering, you refine everything you do. Okay, that's what a Hauptteilverteilung is. So this is a Hauptteilverteilung. Verteilung. I misspelled it. Hauptteilverteilung. Is such a thing, and this is the space of all. This is the space of all Hauptteilverteilung. Okay, now I'll write it in English. principal part. Distribution. And I never think in English in this setting, so I may have translated that wrong. Somebody's here. What about Prabhat? Do you know, you say distributions or not? Principal part?
I just said principal parts.
Okay, maybe just principal part. Okay. But Verteilung is the German word for distribution, so I mean, it's distributing, it's very good. You have this. Okay. So at every point, you have a principal part. It's the support of these things is discrete. You have a map. You have a map from meromorphic functions on U to the Hauptverteilungen on U, Hauptverteilungen on U. So N gets mapped to its principal part. I'll write the word in English so we don't get confused. The principal part distribution of N. Let's say, let's call this map H. And problem 3 is determine. You want to understand this map, the image of H is an example of the problem. You should understand, of course, that H of M1 plus H of M2 is equal to H of M1 plus H of M2. Here, I got it right without making a mistake, first of all. Right? You're just adding the principal parts at a point. Right? Here, it's an additive group morphism. And here, you were asking about the star. Here, I can take the constants, I can take zeros, so I don't have to put any star. You put the star there because you're thinking multiplicative. Okay. This you can call the Mittag-Leffler problem. It was really Weierstrass who called attention to this, but he had a student involved in this project. And the first problem, where is every meromorphic function a quotient of holomorphic functions, you can call, if you wish, the Poincaré problem. Poincaré asked this question in many contexts. So many great mathematicians have asked these questions. Problem 1, is every meromorphic function a quotient of 2 holomorphic functions? Problem 2, is every divisor the divisor of a meromorphic function? Or what divisors appear as divisors of meromorphic functions? Problem 3, what is every principal part distribution, the principal part distribution of a meromorphic function? Right? These are questions about certain groups, whether the group morphisms, if they're subjective or not, and so on. Okay. These are the basic problems that guided thinking in complex analysis. Let me just tell you, before, let me see, we should take a break now. Well, let me tell you while we're giving you some complex analysis names. For X, a one-dimensional complex manifold, everybody here is taking, either has taken the course, manifold courses, or is taking the course now from Professor Petra. It is completely clear what the definition of complex manifold is. It says that the transition diffeomorphisms are holomorphic or bihomorphic. They preserve homomorphic. Okay? So it's completely clear. We will talk about this in detail. This is called a Riemann surface. If it's connected. So, it's called a Riemann surface. You have pictures of such, but don't forget, a domain in the plane is also a Riemann surface. It's very important. It's probably the most important Riemann surface. Yeah? Why should it be a sphere? Why should it be a torus? Why should it be all of these other things? The domain in the plane is just as good. Okay. So we have a one-dimensional complex manifold. If X is compact, if X is compact, then as a differentiable manifold, it looks like a handle. We call it a handle body. It looks like something like this. A handle body. As a differential manifold, you hook together a bunch of handles. This is a classification theorem. The differentiable classification of one-dimensional complex manifolds is a joke. It's not easy to prove, but the answer is a joke. There's one invariant, the number of holes. The number of holes is called the genus. Again, if you have a complex manifold of dimension 1, you can forget it and say it's a differentiable manifold of dimension 1, and ask what is it, and I'm saying the only invariant is the genus. However, of course, there are many complex manifolds to the same genus. Many. That's very important to think about. So anyway, that's the differentiable thing. And in this case, there are no holomorphic functions except for the constant. Why? Because every holomorphic function has a maximum someplace. It's a compact thing. Well, okay, it's a constant. So the problem one vanishes. Because there are no interesting holomorphic functions. Right? Only the constants, because of the maximum principle. Problem one is right here someplace. Well, there it is. This is every function a quotient of holomorphic functions. Okay, that's interesting. Problem one vanishes. Problem 2 and problem 3 are the most important, in fact, essentially the only important problems in the first steps in complex analysis of compact manifolds. Okay. So problem 2 has one of the most beautiful answers of any mathematical theorem I know, and I will explain it to you. This is what I call Abel, this is a Norwegian mathematician, Jacobi Berlin theory. Answers this problem in an incredibly beautiful way. Let me just give you a hint of the beauty of this. If I have a compact Riemann surface, it generates, believe it or not, it generates a beautiful group. Believe it or not, this highly nonlinear thing generates a beautiful group. You can add points. You leave the Riemann surface and go someplace else. But you can add points, and the answer to this problem is determined by a very simple statement in that group. This is the fundamental theorem where Jacobi made many contributions, but of this man named Abel. And problem number 3, this is the problem. This is answered by so-called Riemann-Roth theory. This was a deep theorem proved by Riemann, outlined a proof by Riemann that was not completely finished because his analysis was not formal, as pointed out by Weierstrass, but Hermann Weyl completed this. And these two theories now, in the compact case, I want to explain to you in this course as two of the most beautiful theories in complex analysis. This is for compact. And for non-compact, I will explain the answer for non-compact. All problems are answered with an answer yes. All answers are yes. This is also a very deep, beautiful theory. The basic theorem is due to a pair of people called Heinrich Benke and Carl Stein, actually both friends of mine, and well, they're long gone now. And another friend of mine proved really the way to look at it. This is a French mathematician by the name of Malgrange, and the way to look at problems 1, 2, and 3 in the non-compact case is from partial differential equations.
By non-compact, you mean that the subdomain of complex plane are also compact Riemann surface remove some points.
I don't know what you're saying.
For compact Riemann surface remove some points to
So he's asking, wasn't there a partial solution to this for domains in the plane? That's what you're asking. Yes?
Yeah.
And Benke and so on. I'm not sure exactly. This may be before Benke and Stein, but it's not so clear to me. Maybe Weierstrass. So, of course, Weierstrass solved these problems for the complex plane itself. Yes, with the so-called Weierstrass products and so on. And Mittag-Leffler solved these problems for the complex itself. Yeah. But it's very deep analysis. You have to prove a deep Runge theorem, approximation theorem. And the only time any kind of general approximation theorem was proved was the Benke-Stein approximation. But it's the wrong proof, because the proof should be a partial differential equation proof, and that's the proof of Malgrange. So I would like to explain my goal, and this is almost, now we reached the second half of this course. I want to explain to you how these problems are solved. Okay? This is no longer Mickey Mouse mathematics. This is hard mathematics. And I would like for you to understand what hard mathematics is. Okay? In my lectures in the physics seminar, I will explain in 2 lectures the Atiyah-Singer index theorem, which proves the higher dimensional version of Riemann-Roch theorem, and gives you an idea of what's going on in real mathematics. It's very interesting. Okay, thank you. Let's take a break till, tell me how long you want to break.
Half an hour.
Half an hour. Is that okay? Something like a half an hour? We have a second lecture.